Okay, so give me just 1 second here. Okay, we'll use, as our first example, we'll use a linear parent function. This is kind of a dumb one in a way, because lines, we could almost treat lines separately. We've spent so much time on lines that we really don't need to think about lines as having a parent function and being tweaked. We can just think about lines in terms of, slopes and y-intercepts and things like that. But we'll add it to the list, even though we really won't use it very much. This will just be kind of our warm-up. All right, so if we want to come up with the most basic line, would everybody agree the most basic line that we could draw would just be y equals x? Now I'm going to write these as using function notation instead of y, though. So there's our most basic line. Wouldn't that, if I graph that thing, it's just a line with a slope of 1. So there it is, pretty boring, right? The important points that it goes through, well, we know that this one goes through the origin, so it goes through the point 0, 0, it goes through the point 1, 1, and it goes through the point -1, -1, right? So there's our picture with the key points. And you tell me, what's the domain of this linear function? Abby, what's the domain?
It would be all real numbers.
All real. Go ahead. Oh. Go ahead. I'm sorry, I cut you off.
Yeah, negative infinity and then positive infinity.
Good. So that's our way of saying all reals with interval notation. What about the range? Adelaide, what's the range of this function going to be?
All real numbers.
All real numbers. Good. What's our x-intercept going to be, Alan? You know what? I don't even care about that. Let's not even mess with. We won't even mess with this stuff. Yeah, we won't even mess with that part, and we won't mess with this part for now. We'll come back to this stuff later in class. We'll just focus on domain, range, key points, end behavior, and whether it's continuous or discontinuous. Okay, how about the end behavior? Now, this is a little bit strange. This is a different concept, right? The end behavior is asking the question, what does this do at the left end of the function and the right end of the function? So we'll always let's do the right first here, right? The right, actually, doesn't matter which way we do this. We'll do the right first. So I'm going to put an R by this one. So that's our right end behavior. Now, what do we mean by that? Well, there is no end to this graph, is there? This graph is going to move off to the right forever. The ant could walk to the right forever. And as he does so, he's walking up the entire time, right? So the way we would say that then is as x approaches infinity, and that arrow means approaches. Okay, when we see an arrow like that, that literally stands for the word approaches. Well, we can't get to infinity, right? So all we can do is approach infinity. What does that really mean? As x approaches infinity, it just means as the ant goes as far as you want to go to the right. If you just keep going and going and going, what's the behavior of the function going to be? So we're asking the question, as x approaches infinity, what does f of x or y approach in this case? What do you think, Chloe? What do you think an appropriate answer would be on this function?
I
have no idea what it all could be.
You're exactly right. It would also be infinity, right? Because and think what that says. As an ant goes infinitely far to the right, he is also at the same time going to be moving up infinitely far based on the shape of that graph, isn't he? Right? That's all it's asking. Okay. So as x gets big without limit, so does y. Okay, what about the left side of this? As now, what would we be approaching on this graph? If we want to go to the left end of the function, which doesn't actually exist, right? So what would we be approaching there, do you think, Dawson? So as the ant's going to the left, what's the x value of the left end going to be? What's he approaching? Negative infinity. There you go. Good. So as x approaches negative infinity, well, what would y approach based on the shape of this graph? If the ant goes to the left forever, what's his y value doing? Dawson? Say it again. Negative infinity. Good. Okay. And is this function, what do you think, Delub, is this function continuous or not? And the way we test that is, if it's continuous, I could draw the entire graph without ever picking my pen off the board. If it's discontinuous, I have to pick my pen up at least once. What do you think?
Would it be continuous?
So it is continuous, yep. Okay, good. Now let's just look at some other, you kind of get the idea then of what we're going to do for each of these functions, right? For each of these functions, we're going to fill in those blanks, and let's go ahead and we'll cross these out if we're not doing those. Okay, absolute value. So our function here is going to be f of x equals the absolute value of x. Okay, so first of all, what's that look like? Well, here's the picture of an absolute value graph. An absolute value graph is a V. The vertex is at the origin. The right leg has a slope of 1, and the left leg has a slope of -1. So the key points it goes through then, maybe we'll color code these a little bit. So this point right here, the purple point is the origin, right? That's a really important one. The green point right here goes through the point 1, 1. And the orange point over here goes through the point -1, +1. Okay, and then we just that gives us the shape of the function. Those are some easy points to use in graphing the function, kind of plotting it. Okay, so the domain. What's the domain going to be this time, Jace? Of an absolute value function. Questions for Jace? Oh, there it is. Sorry. Oh, okay. Okay. I'm going to skip you then. You're having troubles. Kendall. What's the domain?
Wait, what's the question?
Domain for this absolute value function.
Is it just positive infinity?
The domain. Now, the domain's a set of x values.
Oh, okay, then just negative. Or I meant the sideways 8 infinity.
Okay, right. Okay, so we're going. So you're gonna tell me what goes where. That's fine.
Oh, negative infinity, comma infinity.
There you go. And we can just say that as all reals. Okay.
Okay.
What about the range on this one, Carrie?
It would be 0, infinity.
Okay, 0, infinity. What kinds of symbols do I need?
A parenthesis over infinity. Would it be a bracket?
It would. It would be a bracket. How come?
not to include 0.
Good, because I'm including the 0.00, aren't I? Yep, very good. Okay, and so end behavior. Next issue, end behavior. Liliana, what's my left end behavior going to be? Oh, sorry, we did right, didn't we, last time? We'll be consistent, so this is going to be my right end behavior. Let's go.
Would it be infinity?
Okay, so as x approaches infinity, good, because we're going to the right forever, what does f of x approach?
Infinity.
Okay, good, good. What about my left end behavior, Maria? As x approaches,
Negative infinity.
f of x approaches
Infinity.
positive infinity. Good. Okay, is this function continuous or discontinuous, Natalie? Questions for Natalie. Is it continuous or
Discontinuous?
how come?
Because it's not the straight line.
Okay, but once again, the test is, it's the pen test. Can I graph the function without taking my pen off the board?
Oh, yeah.
Okay, there you go. So it must be continuous then, right?
Yes.
Okay. Okay, quadratic. You remember this from last year, probably our most basic quadratic function would be y or f of x just equals plain old x squared. And that's going to give us a point at 0, 0, which is the vertex. It's going to give us a point at 1, 1. And it's going to give us a point at negative 1, 1. And then I just have to graph the function that, the parabola that goes through those points. So it looks sort of like that. You get the idea, right? Instead of a V, it's a U, right? The absolute value is a V shape. This is a U shape. So I need the domain of this, Olivia.
Negative infinity to infinity.
Okay, good. So all reals. While you're at it, what's the range, Olivia?
Would it be 0 to infinity?
Good. And what symbols do I need?
Bracket for the 0 and then a parentheses.
Good, because we're including that point. Very good. So don't worry about this stuff. The end behavior, Pagan, what's my right end behavior going to be for this function? As x approaches what?
Infinity?
Good. F of x approaches?
Is it still infinity?
Yes, it is. Good. And my left end behavior, Rebecca Gershom? What am I going to get for that one? As x approaches?
Negative infinity?
Very good. F of x approaches?
Infinity.
Infinity. Good. Oops. And is this function continuous or discontinuous? Rebecca Edmonds.
It's continuous.
It's continuous. Good. Okay. So now we move down to a cubic function. Okay, cubic function, the most basic cubic function is f of x equals x cubed. That's got key points at the origin, at the point 1, 1, and at the point negative 1, negative 1. And the graph looks like this. Okay? So, Miss House, domain.
It would be infinity, right?
Right, all reals. What about the range?
Yeah, all reals.
There you go. Okay, we'll skip this part. End behavior. Abby, what's my right end behavior going to be?
So as x approaches infinity, it would also be infinity, right?
There you go. Okay, and let's see, Adelaide, what about my left end behavior?
Infinity and
As
and
say it again. As
negative, negative infinity and negative infinity.
Perfect. Okay, continuous or discontinuous, Alan? Alan, continuous or discontinuous?
Did you see my name?
Yeah, I did. Yeah,
I'm so sorry.
that's right.
Continuous.
Continuous. There you go. Yep. Okay, square root. Now we get into some weirder ones. Square root looks like this. Square root, its special point ends up being a starting point, right? So it starts at the value 0, 0 at the origin, and it goes through the point 1, 1. So it looks like this. Okay, but it's a little different looking graph, isn't it? Oh, by the way, the parent function would be f of x equals the square root of x. Okay, so this time, now what's the domain of this one, Chloe?
It would be the bracket 0 and then infinity.
Okay, how about the range?
Would it be all real numbers?
The range, the y values? Look again.
Yeah.
Look again.
Mm.
The y values now. If I were to project that whole graph onto the y-axis.
Oh, it would be the bracket 0 and then infinity.
There you go. End behavior. Now this is some different end behavior this time. A little different. Let's see. Dawson, what is my right end behavior on this one?
Would be
Yeah, as x approaches infinity, f of x approaches infinity. Now, how about my left end behavior, Luke? What's that going to look like? There is a left end point. So as x approaches what?
As it approaches 0?
0, y approaches
0.
0. Okay, so there's my left end behavior. It actually does get to that point, doesn't it? Sometimes we would even say that maybe this one doesn't have interesting end. I mean, you could describe this different ways in math. Some people would say there is no left end behavior because it's not infinite, right? But we'll treat it this way, and that's fine. Is this function, now here's another one. Is this function continuous or discontinuous? Because we could have a discussion about this, and you could probably argue both ways on this, but I think that the notes are wrong on this one. I'll tell you that. In fact, I know they're wrong. What do you think the end behavior? Jason, did you get your mic working? Oh, doesn't look like it's working. Kendall, what do you think? Is this continuous or discontinuous?
I think it might be continuous because you can keep doing bigger and bigger numbers?
I would agree. You can draw this thing without ever taking your pen off the board. So I would say that this is continuous function. Now it's continuous on an interval. The notes say discontinuous, but I'm not agreeing with that. I'm saying continuous. So we're going to go with continuous on this, even though the notes say differently. And when we get to calculus, we'll defend why I say that. Okay. And once again, it fits. There are no on its domain. 0 to infinity, I can graph this thing without picking my pen off the board one time, right? Okay, moving on. Cube root. Cube root looks like this. So cube root, we've got points at the origin. We've got a point at 1, 1. And we've got a point at -1, -1. And the shape of this thing is like this. Okay? Something like that. It's supposed to be arrows. And we write this with, it's a radical where the index of the radical is a 3. Okay, domain of this one. Where did we leave off here? Carrie, what's the domain? Okay, and the range? Okay. The end behavior on this one, Liliana? What's my right end behavior?
Wouldn't that be to the right
Yeah,
of infinity?
okay, and good. As x approaches infinity, f of x approaches infinity. While you're at it, how about the left end behavior?
Negative infinity.
And
Yeah.
there you go. Good job. Continuous or discontinuous, Maria?
Continuous.
Continuous, yes. Okay, a reciprocal function. The reciprocal function is this one. F of x equals 1 over x. Okay, now what about its points? Its key points are at 0, 0, at 1, 1, and -1, -1. And here's what the graph looks like. I want you to notice something. I called this a key point, and yet it never even passes through that point. Why do you suppose it's a key point there? Anybody?
X is 0, f of x is 0.
But that's actually not a point on the graph. I should say that. So this is, let me make a note of that. So this is not on the graph.
Because that's the point that it's flipped over.
Yeah, it's the point of symmetry, isn't it? We haven't talked about symmetry yet. We'll get on to symmetry later in the year. But this is the point of rotational symmetry. If I put a tack in the, say this is printed on a piece of cardboard. If I put a tack in the cardboard right there, and I spin this thing 180 degrees around, it would line up perfectly, wouldn't it? Right? So we'd say it has rotational symmetry then. There's another thing we could say about this. The behavior, we have what are called asymptotes here, right? These are asymptotes are lines that the function butts up against but never actually gets to, right? And so we have and we'll talk a lot more about this later in the year. but we have a vertical asymptote right here on the y-axis that the function pushes up against it but never gets there, and we have a horizontal asymptote on the x-axis that the function approaches but never gets to, right? So that's that asymptotic behavior. I'll put these in here. There we go. So there's a vertical asymptote. And it's just the line x equals 0. Here's a, so there's my horizontal asymptote. And that's the line y equals 0. It's the x-axis. Okay? All right, so this is a little trickier one. What's the domain going to be for this function? What's the domain for my reciprocal function? What do you think, Maria? What's the domain going to be for that one?
Does it ever reach 0?
Say it again.
Does it ever reach 0?
Never does it? It pushes up towards it from the left and the right, but it never gets there, does it? So what do you think the domain is on this one?
Everything except 0?
Everything except 0, exactly. So one way to say that is literally x is not equal to 0. That implies everything else but not 0. Everybody get that? Another way to write that, if we wanted to write the domain in a different way, we could also write it like this, right? We could say something like, right? I could just list all the other numbers except 0 is the one that skipped. I put a comma in the middle, or I could put a union symbol in the middle, depending on, either or. Okay, but isn't it easier just to say x is not equal to 0, right? Okay, what about the range? Natalie, what's the range going to be on this one then? Questions for Natalie. How about Olivia?
Would it just be negative infinity to infinity or anything?
Okay, but is there a value in there that never gets touched?
0.
0, yeah. Okay, so how could I say that?
X is not equals.
But this time we're talking about range, so it should be.
Y is not equals.
There you go. Good. So y is not equal to 0. Exactly. Everything else is fair game, but 0 is the one that's skipped. Okay, so what about my end behavior this time? So as you tell me, what's my right end behavior going to think? This is tricky. Can you make sense of this? What's my right end behavior going to be this time?
I'm not sure.
Okay, so if an ant walks infinitely far, can an ant walk infinitely far to the right on this function?
Yes.
It can, right? So I can put an infinity there. As x approaches infinity, what y value would the ant be approaching if he walked along this graph infinitely far to the right?
Negative, or I don't know.
Look what he's doing. He's walking along this function, and he's just getting closer and closer and closer to a certain value.
He can't reach 0 though, right?
Right, but that's what he's approaching. And that's what that
Okay.
arrow means, is
Yeah.
approaching. Yeah, I understand. Okay, I get where it's tricky, isn't it? The concept. As x, but he can't get to infinity either. But as the ant approaches infinity, his y value approaches 0. We spend a lot of time at the start of calculus talking about limits. And that's really what this is. This is a limit. The way we would say this, by the way I would say that in calculus, so in a couple of years, we would say something like this. We would say the limit, that's just LIM, the limit of f of x as x approaches infinity is 0. That's how we'll write it in 2 years in AP Calculus, okay? What about the left end behavior on this one then? What's the left end behavior going to be, Rebecca Pearson? As x approaches,
As x approaches infinity, or negative infinity.
negative infinity. Good. What does f of x approach? 0. There you go. And the asymptotes. Okay, we already talked about the asymptotes. The asymptotes are x equals 0 and y equals 0. The x-axis and the y-axis, right? In order, the y-axis and the x-axis.
Well, what are the asymptotes?
So the asymptotes are the horizontal line and the vertical line that the graph pushes up against but never reaches.
Okay.
Okay, and notice that the point of intersection of the asymptotes is the origin, right? And that's really the most important point in graphing this thing, is that point of symmetry, okay? All right. Let's see. Exponential and logarithmic, and we're done. Okay, so an exponential function. We're going to take the exponential function. Which one do they take here? They do, oh man, 2 to the x? Okay, that's kind of dumb. Okay, we'll do that though. So for our later on in the year, and this will be more of a next year thing, you're going to use a different exponential function most of the time. We'll use a base that we're familiar with. We'll go 2 to the x. In the future, you're going to do something different. In the future, we're mostly going to talk about e to the x, where e is the natural constant. Okay, just kind of like pi. But we'll do 2 to the x for now. Okay, so here are the points that the key points that this one goes through. This one goes through the point 0, 1, and it goes through the point 1, 2. Okay, yeah, we'll do that. And it looks like that. Okay. So what's the domain of this one going to be, Rebecca Edmonds?
All real numbers.
Yes. And while you're at it, how about the range? You have any questions about the behavior of this thing?
So it doesn't ever intersect with y equals 0?
Okay, good question. And the answer is it does not, because we have an asymptote there. We have a horizontal asymptote at y equals 0. So now what's that tell you about the range?
would be bracket 0, infinity.
Okay, but if I have an asymptote there, it can't ever get to 0.
Oh, parentheses.
There you go, parentheses. Good. And let's see. We got it. Sarah, what about end behavior? So what is my right end behavior on this one?
As x approaches infinity and y approaches infinity.
Okay, and my left end behavior?
As x approaches negative infinity, y approaches 0.
There you go. Good. Continuous or discontinuous?
Continuous.
Continuous, yes. Oh, you know what? I think we forgot that on the last one. Did we ever write that part down? Oh, we didn't. Obviously, the reciprocal function, finally, we get one that's different. Is the continuous function, or the reciprocal function continuous or discontinuous? Go ahead, Sarah.
I would say discontinuous.
It is discontinuous because I have to pick my pen off the board to move from one part to the other, don't I? So finally, we got one here that was discontinuous. Okay, and then the last one is the logarithmic function. Okay, the logarithmic function it's got a strange kind of symmetry with the exponential function. It has reflective symmetry about the line y equals x, which means that these are inverses. We'll get into all that stuff later. So this is how we write it. And I think, in order to make these, okay. We're gonna do the natural log function. Okay, so it's a little bit different, which is the inverse of e to the x. So we write that as, that's a cursive, it's a script cursive, or script L. So it's ln, that's an L. The natural log of x. And here's what it looks like. It goes through the point 1, 0. And it looks like this. It's asymptotic. Gosh, this stupid pen is driving me nuts. It looks like that. Okay, so it's asymptotic on the y-axis. So that's the asymptote. X equals 0. Okay, and what's my domain going to be for this one? Abby?
So it would it be 1, infinity or 0?
Okay, you tell me. So the asymptote is the y-axis, so it can get arbitrarily close to that, but it can never reach it.
Oh, okay. So it would be parentheses and then 0?
There you go. There you go. And what about the range?
It would, that would be, so it would be kind of opposite of it because it would never, I'm
Right.
confused on that one.
Right. Okay. So this is one where it's going to continue to rise. It rises very slowly, but it's going to continue to rise forever. And so this is one. The graph is a little misleading. It's just all reals for the range.
Oh, okay.
And the end behavior, Adelaide, what's my right end behavior on this one?
Would it be infinity?
Good. As x approaches infinity, f of x approaches,
And 0?
no.
Mhm.
As x approaches infinity, what's the
Oh,
function?
it's infinity.
There you go. There you go. Good. And then what about my left end behavior? As x approaches
0?
0, good. F of x approaches,
Negative.
there you go. And would everybody agree that this is continuous? On its domain, okay? All right. How are we doing on that? Good? Okay. 45, yeah, that's a good place to stop for today, I think. So what I have to build, the problems that all these textbooks provide are just really bad on these. So I'm gonna have to go in and program some questions. I'm not really used to this programming environment like I am Moodle. So it's gonna probably take me a few hours to do that. It's gonna be this afternoon. So it means this one probably won't be up until this evening. Okay, and it's a really quick assignment, but it's one I want you guys to go through so you can get a little practice just memorizing these graphs. So this is a light day. We'll talk about transformations on Friday, and that's a little bit. There's a little bit more going on there. But I'm gonna give you guys kind of let you catch your breath a little bit on some past assignments, and this will be a short one, and then I'll give you a little bit more on Friday. Okay. Sound good? All right, so I'll tell you what, if you want to, if you have questions, stick around, but I'm just going to let you go here. How early is it? 5 minutes. Yeah, I'll let you go. I mean, if you want to just go stretch a little bit, I never do this, so Merry Christmas. Get up, have a snack, stretch a little bit, unless you have some questions, and I'll just be here. And you can go ahead and hang this up if you're done, and I'll see you on Friday. I'll be here after school, too, if you have a need for anything.
I actually have a question.
Yeah.
When's the latest that we can retake test?
I don't really. I think sooner is better. Like, which one are you wanting to retake? The test 2?
I think
Test. Oh, that's fine. Yeah. No, you can do it after Christmas. It's fine. Yeah. No sweat. Yep.
the day I have is Friday.
No, you've got. I'll give you. You can come back and do it after Christmas too if you want to. That's fine. Yep. No problem.
Thank you.
You betcha. Bye.